Hey Chem 20s, it's Mr. Jukely here again. Today we're going to, we're going to roll through a whole handful of things here. Just so you know, this is going to be our last curricular video for this whole COVID-19 crazy times we're in. I want you to know that I'm really proud of you for sticking with things and for getting to this point. So finish strong, keep up the good work, and yeah, you're going to go places, I can tell. So we are actually going to skip over a bunch of stuff here. And by skip over, maybe skim over is a better word actually than skip over. Actually, what color? Oh yeah, okay, that'll work. Okay, so a lot of this stuff, what page are we even on here? Let's get that first. We're on page 19, currently on page 19. In the last video, we actually talked a lot about this kinetic molecular theory of gases. That's the theory that everything's made up of tiny particles. Those tiny particles are in constant motion. We know the difference between, solids, liquids, and gases. We're kind of focusing on gases, tons and tons and tons of space in between the gases, and they're moving really, really quickly. We understand the temperature and the speed of the particles, or the kinetic energy of the particles, are closely related. And because we've talked about a bunch of this stuff before, we're going to kind of skip over it. Right? Actually skip over it in this case. So kinetic molecular theory does explain why gases are compressible, explains the concept of gas pressure. Already talked about those couple things. Explains Boyle's law and explains Charles's law. Absolutely no problem. If you want to have a quick read, by all means, go ahead. But we did talk about most of that stuff before. Oops, that's a little bit too far. So the next one, the law of combining volumes, I'm going to kind of leave this one up to you. If you want to check it out, that's cool. If not, that's cool too. There's one thing that I'm going to highlight for you. One thing that I'll highlight for you. But that's about it. All we're really talking about in this case is at the same temperature and at the same pressure, a gas will take up the same volume. The same amount or number of moles of gas will always take up the same volume. Doesn't matter what type of gas it is. So where's the one thing that I want to highlight here? There it is, and that's pretty much what we just said. So equal volumes of an ideal gas at the same temperature and the same pressure contain the same number of molecules. So let's say we're dealing with STP. You remember that 0 degrees Celsius and 101.325 kilopascals. So if I have 1 liter of any type of gas, it would be the exact same number of moles. So it doesn't matter if it's water, oxygen, hydrogen, methane, ammonia, hydrogen, nitrogen, you name it. If it's at the same temperature, the same pressure, and you have the same volume, it's the same number of moles. Which kind of leads us to like everything that we're dealing with here, which is all stoic, and leads us to the idea of molar volumes. So molar volumes are just a couple really specific ones. Again, we're skimming this like crazy. You want to go into more detail? By all means, go into more detail. If you kind of get the idea of what we're talking about right now, it's more than enough. So at STP, which remember is 0 degrees Celsius, 101.325 kilopascals, the molar volume of gas is 22.4 liters per mole. What that means is when my volume is 22.4 liters, that's the same thing as 1 mole, and this is our conversion factor. That's the thing that we would do stoic with, essentially. So canceling out units to get what we want. At SATP, doesn't matter what type of gas it is, it's going to be 24.8 liters for every 1 mole of a substance. Cool, so just another conversion factor. That's all there really is to it. So there's examples, there's practice. Feel free to try it out if you want to. If you don't want to, whatever. It's if you get the idea from what we just talked about, that's fine. What you definitely should have a look at and do a bit of practice with is, let's see, page 24. We're talking about the ideal gas law, and we're going to talk about real gases versus ideal gases. So first and foremost, an ideal gas is a gas that obeys all of the gas laws perfectly. Obeys all the gas laws perfectly. Doesn't matter what condition it's in. It's always adhering to those gas laws that we talked about in the last one. So Charles's law, Boyle's law, Guy-Lussac's law. So in other words, they never ever condense into a liquid. Their graphs are perfect no matter what. Temperature, pressure graphs, volume graphs, they're all perfect graphs. The other thing is the ideal gas is composed of particles of zero size and they have no attraction to one another, which we know is not actually that realistic. Real gases, so this is our everyday life gases like the air that I just breathed into my lungs. They do condense into liquids eventually at low enough temperatures, at high enough pressures, and the particles are attracted to each other, at least a little bit. Um, Therefore, they don't follow the gas laws perfectly, like not exactly. Um, the thing that you need to know is that real gases deviate most from ideal gases as temperature decreases and pressure increases. So in other words, if the particles are far enough away from each other, it behaves like an ideal gas. But if you squeeze those four particles down and they get way too close together, then all of a sudden it's not going to behave like an ideal gas because they're going to take up some sizable space. Or if you cool it down, and cooling it down would bring those particles closer together again as well, slowing them down so they actually interact with each other. But if they're hot and they're under low pressures, they've got lots of energy, they don't interact with each other, they take up a ton of space, oh yeah, they're fine. They're acting like ideal gases. So again, ideal and real gases. So kinetic molecular theory assumptions for ideal gases. So this is what we are assuming as Chem 20 students gases behave as. This is what ideal gases. So the gas molecules are very, very, very far apart compared to their size. In other words, their size is negligible, which means they have zero size. Whereas with real gases, under high pressures, the molecules are closer together and their size becomes significant, which means they don't have zero size anymore, right? Okay. Gas molecules are in constant random motion because there's no forces acting between them. But as the temperature decreases, the molecules slow down. At some point, they slow down enough that they can actually stick together and become a liquid. That's our real gas. And then finally, gas molecules undergo perfectly elastic collisions, which is why no energy is lost. Perfectly elastic means, again, no energy is being lost whatsoever, but there's no such thing as a perfectly elastic collision. There's no such thing. So in other words, if they're losing a little bit of energy, they're going to lose a little bit of pressure every single time a collision goes through. Now, the really important thing that I would probably check out is real gases behave the most similar to ideal gases when they're at low pressures and high temperatures. The size of the molecules do also affect the deviation from the behavior. So like if you have a really, really, really large gas molecule, it'll deviate quicker than a really, really small gas molecule. But we assume that they are all ideal, is essentially what we're looking at. Now, when we kind of cram together Boyle's law, Charles's law, Avogadro's hypotheses, we come up with a new equation. So PV equals nRT. PV is equal to nRT. My Chem 20 teacher made me stand on top of a desk. He got everybody in the entire class to stand on top of a desk and start chanting PV, nRT, PV. So you wouldn't, I still to this day remember that. So everything's fairly straightforward. Like P, you know, is pressure, needs to be in kilopascals. V is in volume, or sorry, is volume, needs to be in liters. N is the amount, needs to be measured in moles. R is a constant, so I'm even just going to draw an arrow over to here. So it's a constant, and T is our temperature that needs to be in Kelvin. So R, the constant, 8.314 kilopascals times liters over moles times Kelvin. So the constant, like people understood the relationship between pressure, temperature, volume, moles, all of those different things, but they didn't necessarily have an equal sign. A relationship is not an equal sign. The constant allows us to have that equal sign. So this is a little tiny bit of bonus material right here. We're going to show you how to do it anyways, just for the practice. If you can do it, that's great. If not, that's fine. So some things that you'll see in practice is, can you solve for the molar mass of something? A molar mass. So we've got PV equals nRT. And then we've also got a formula, N is equal to mass divided by molar mass. So the thing that's going to relate this to us is N is equal to mass over molar mass, and N is also right here in the formula. So what I'm going to do is I'm just going to take this, and I'm going to put it exactly in there where N was, because we know N is mass divided by molar mass. Cool, so I'm going to rewrite this. P times V is equal to mass over molar mass times RT. Perfect, so we just replaced N with what N means. Now if I'm looking to solve for the molar mass, I'm kind of running out of space here, so I guess I'm going to go this way. Molar mass, let's see, it's on the bottom. I'm going to do the shortcut rearranging, but you do need to know how to rearrange equations. So I'm just going to switch place with molar mass and PV. So molar mass, capital M, make that big and jagged so we know it's capital, is equal to lowercase m times R times T over PV. So if we're looking for molar mass, well, there it is. We've got it, right? Okay, the other one asks for density. Density, remember from grade 8 or whatever, it's mass divided by volume. So mass divided by volume. So I'm going to stick with this one that we've got right here. So P times V is equal to mRT over molar mass. So all I need to do is I need to rearrange and solve for mass divided by volume. So let's see, I've got mass on the top over here. So I want to slide volume down, or divide both sides by volume. And I'm going to slide or multiply molar mass up. So let's see. I'm going to have M over V is going to be equal to P times molar mass. Hold on, did I do something funny here? P times molar mass, no, I'm good, over R times T. And again, that is molar mass, so I'll make a big capital M. Maybe I'll put this little squiggly thing on there so you know that it's mass. And we know that mass divided by volume is density. So in other words, density is equal to pressure times molar mass divided by R times T. So the constant divided by the temperature in Kelvin. Cool. So anyways, you may use these, you may not. It's depends on where you get to with the practice. Honestly, if you know how to use this formula and understand the ideas of this formula, you're golden. So things that I'm going to get you to do. I'm going to get you to answer question 1, question 2, because it's kind of a review of exactly what we just talked about. Let's see. Interaction between molecules and real versus ideal. All we'll say with this is, so unlike an ideal gas, a real gas condenses to a liquid when the temperature is low enough. Why does this happen? So, and what does this say? So real gases have intermolecular forces. So in other words, they're attracted to each other, even though it is very slight. Right? It's not a huge one, but it is very slight. So I'll answer that one for us. And let's get into question 4, an actual example using our formula. This is a bit of a doozy. So an airbag is activated in a collision, and this is actually kind of cool. Most people don't know that airbags are actually chemical reactions, the reason that they fill up so quickly. Even if it was like a compressed air or something like that, it wouldn't fill up quick enough. It's got to be a really, really fast chemical reaction. So anyways, airbags in your cars in a collision, sodium azide rapidly decomposes to produce nitrogen gas. Cool, I have no idea what sodium azide is, if I'm being 100% honest with you, but I know it produces nitrogen gas. Chemical engineers carefully choose the quantity of sodium azide required to produce the required chemical amount of nitrogen gas. That was a bit of a mouthful for me. Use the ideal gas law to predict the amount of nitrogen gas required, and here's the actual question, starting right here and going that way. Use the ideal gas law to predict the chemical amount of nitrogen gas required to fill a 60-liter airbag at a pressure of 233 kilopascals at a temperature of 25 degrees Celsius. So let's summarize that last little bit here. We want to predict the chemical amount of nitrogen. So N is our question mark. Trying to figure out the amount of nitrogen. The volume tells us right off the bat is 60 liters. The air pressure, or not air pressure, the pressure is 233 kPa, and the temperature is 25 degrees Celsius. Now I'm being very specific with that degree Celsius. Do we really want degrees Celsius? No, needs to be in Kelvin. So I'm going to add 273.15. So it should be 298.15 Kelvin. Nice. Okay. The only thing that's missing from this is R, which was 8.31. Ooh, I better look it up real quick here. 8.314. Just better to be safe than sorry. And then it's got this weird unit, so kPa times liters divided by moles. Oops, Kelvin. There we go. Okay, so let's go through my formula, PV nRT. Thank you, Mr. Devon. He's the one who made me chant that. PV is equal to nRT. I'm looking for N, so let's go through our rearranging here. I'm multiplying it by R, and I'm also multiplying it by T. Anytime I want to move something, I need to divide or work in opposites. So in this case, I'm multiplying, so I need to divide both sides. So R over R cancels, T over T cancels. So I end up with N is going to be equal to PV over RT. Cool, so the pressure, 233 kilopascals, times the volume, 60 liters, divided by our constant, 8.314 kPa times liters over moles times Kelvin. Bit of a doozy there. And then divided by the temperature, so what did we say, 298.15 Kelvin. Check out what happens with the units here. kPa cancels with kPa. Liters cancels with liters. Kelvin cancels with Kelvin. What's the only unit we have left? Moles, which is exactly what we're looking for when we're looking for amount. So we go ahead and plug the numbers in here. I don't have a calculator with me, which is kind of annoying. So 233 times 60 divided by 8.314, also divided by 298.15. So that works out to be, we get the answer to double check up here, with significant digits, because we had, let's see, 2 was our least number from the question. So we should have 2 in our answer, so that should be 5.6 moles of nitrogen, N2. Cool. We can do one more. I think question 5's a tiny little bit trickier, so I think we'll look at question 5, and, well, and then we'll see, I suppose, here, hey? Then we'll see. So, at what temperature does 10.5 grams of ammonia gas exert a pressure of 85 kilopascals in a 30-liter container? So I'm going to start again with just kind of my variable list. So I've got the mass of ammonia at 10.5 grams. Let's see. In my formula, PV is equal to nRT. I need N, so I might need the molar mass of ammonia as well. Anytime I'm going to go from amount to that. So let's see. Ammonia is NH3. Ammonia is NH, not ammonium, ammonia. So that's 14.01. Just getting the molar mass, 14.01 plus 3 times hydrogen, so 3 times 1.01, that's 17.04 grams per mole. Okay, we'll keep that in our back pocket for a second. We've got our pressure is going to be equal to 85.0 kPa. We got our volume is 30 liters. And it is asking us for what temperature, so T is our question mark. Nice. So first thing, like we already mentioned, in PV is equal to nRT. So I'm going to do this on the right-hand side of the board. PV is equal to nRT. I need to know what N is. So you can go through and you could do this in one of two ways. You could say N is equal to mass divided by molar mass, right? And use the actual formula for that. Or we could do this in more the Chem 20 way. I could start with 10.5 grams. I want to cancel out grams, so grams has to go on the bottom. I want to end up with moles, so moles have to be on the top. It's 17.04 grams for every 1 mole. Nice, so 10.5 divided by 17.04. Let's see, that's 0.616 ... moles. Nice, so we now know the number of moles. Now let's see, I am looking for, so that's, don't really need that arrow up there anymore. I am now looking for the temperature. So same thing, I am multiplying by N and R, so I need to divide both sides by N and R to get temperature all by itself. So temperature is going to be equal to PV over NR, kind of running out of space, so I have to write a little bit smaller. So the pressure, 85 kPa times the volume, 30 liters, divided by the amount, 0.616 moles, and just keep that, I know it's 0.6169 something, 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 but just keep those in your calculator till later, and then 8.314 kPa, there we go, messed it up a little bit, times liters over moles times Kelvin. And now let's check it out what happens with these units. Liters cancels with liters, kPa cancels with kPa, moles cancel with moles. The only thing we have left is Kelvin, which is perfect for temperatures. So let's go ahead and plug this in. 85 times 30 divided by the answer, so 0.616 yada yada yada, and divided by 8.314. So I end up with 498 with rounding Kelvin. Now, the question asks for what temperature. This is a perfectly acceptable temperature for that. Perfectly acceptable. The answer key, though, gives us in degrees Celsius. So if I wanted this in degrees Celsius, I'd just do 498 minus 273.15 Kelvin. And actually, I wouldn't do 498. I'd do the 497.7. So minus 273.15, just in my calculator, gives me 225 degrees Celsius. So that's an appropriate answer, and that's an appropriate answer. Cool. So from here, you know, honestly, that is probably what we need to know. Well, no, that is definitely what we need to know. For question 6, we're kind of getting into bonus material there. So if you want to check it out, that's cool. 6A and 6B, we're kind of getting into to bonus material there. Question 7, same thing, bonus material. So long story short, as you're doing any of the practice for this, and there's a handful of practice questions, again, do the practice until you're comfortable, but if you're dealing with density, or if you're dealing with trying to solve for molar mass, those ones are bonus material, right? Totally doable, but still bonus material. Cool, so practice for this. Then the only thing that's left, and I'm just gonna kind of skim over this again, is if you have the same amount, it's gonna take the same pressure, right? And it's kind of the opposite of what we talked about before. This is Dalton's law of partial pressure. So if you had 0.3 moles that had a pressure of 0.5, and you had 0.6 moles, well, it would have, that's twice the moles, it would have twice the pressure. When you add them together, right, so 0.9 moles, you'd have, you know, your 1 atmosphere pressure plus your half an atmosphere pressure, your 1.5 atmospheres. So everything is nice, easy ratios, if that makes sense. So again, let's look at the moles. I'm going from 0.3, I'm doubling it to 0.6. What did we do to the pressure? I doubled the pressure. I'm going from 0.5 atmosphere to 1 atmosphere. When you add those two gases together in the same volume, we've now got a total of 0.9 moles, and we've just added the pressure. That's all you really need to know about that. Even if you don't get that, like, whatever. It's important for one lab that we do, but we're not doing a lab. Okay, then the very, very last thing is gas stoichiometry. So gas stoichiometry is exactly the same as every other stoichiometry. You write a balanced chemical equation, you write down all the stuff that's underneath it. You find the moles. I'm even going to write this out. 1, balance equation. It's going to be very shorthand. 2, find moles given. Perfect. So usually you're given enough information to find the moles of something. Because it's gases, you're going to use one of these things. PV is equal to nRT, or STP, SATP, and that molar volume. Cool. So step 3 is to use your mole ratio to find moles required. Cool, so you used your balanced chemical equation, your moles required. And then step 4 is, well, you solve. So again, it could be using some gravimetric, mass is equal to mass over molar mass, or it could be using some of our new stuff. That's a terrible arrow. Some of our new stuff there. So I know I flew through a ton of that stuff there. Absolute ton. The thing you really need to know about is PV is equal to nRT and the ideal gas law lesson. The rest is bonus material. It's totally doable. It's not very hard, but still bonus material. So do what you have time for. And hey, congratulations, Chem 20s. This is the last one, the last video. So I'll talk to you again real soon. Bye for now.